start, I have a great pleasure in introducing Professor Darwish Al-Azmi. He is from College of Technology from Kuwait. He is a scientist working in radon and environmental radioactivity. And he has been a regular visitor and a collaborator with the center. He has spent 3 sabbatical leave in this center, and he has been often visiting our center for collaborative studies. So I welcome him on behalf of Mangalore University and on behalf of all of you.
Thank you very much. Although my time is very tight, but when I noticed you have this workshop, so I did all my best to come here, even for a short time, at least to enjoy the company of the people and get more information about this useful workshop. And I am happy to be again in Mangalore, where I spent 3 sabbatical years. So, and I got very nice papers with Professor Karunakara and his group. So I am happy to continue here again.
This will be good. This will do. So we start with the first great lecture from Professor Shinji Kumar. And excuse me. Many of the participants are requesting for a visit for our other laboratory. Tomorrow afternoon we will have 1 hour schedule, Trilochana. So wherein we take all of them to different labs in batches.
Okay, good morning everybody. So yesterday I gave a lecture on the measurement techniques of radon the proteins. And today my talk will start with dosimetry based on ICRT applications. So here is dosimetry and risk assessment due to radon exposures based on ICRT applications. So let's go. This is the feedback of your knowledge obtained by my talk. Equivalent concentration here is defined radon from activity concentration in equilibrium with the progeny that have the same potential alpha energy concentration, namely PAEC, as the actual present compound of radon or thorium and their short-lived progeny that are not in equilibrium. Understand? Maybe your knowledge is clear now. So equilibrium factor, the ratio of the equilibrium equivalent concentration is to the radon activity concentration. Typical equilibrium factors for dwellings range from 0.2 to 0.6, depending on especially ventilation rate of the dwellings. The other thing, potential alpha energy, PAE, is defined as the sum of the alpha energy of radon 222 or radon 220 and their short-lived progeny in radioactive equilibrium. The unit is Joule. PAEC is defined as the alpha energy emitted from due to radon or thorium activity concentration when radon 222 or radon 220 decays through lead 210 or lead 208 in air volume as a result of a random compound of short-lived radon 222 or radon 220 progeny. The unit is Joule per cubic meter. And touch fraction. This is a fraction of potential alpha energy concentration of short-lived radon or thorium progeny not attached to particles. Working level. You should understand more about working level because in epidemiological studies they use the working level ones. So working level is a unit used for every combination of radon 222 or radon 220 and their short-lived progeny in a liter of air which emits a potential alpha energy of 1.310 to the 5th MeV. One working level for radon is originally defined as 100 picoculi per liter or EERC equal to 3,700 becquerel per liter. On the other hand, one working level for thorium is defined as 275 or 276. It depends on the number. Okay, becquerel per liter. Here, working level mass is a unit for the radon exposure a worker receives during a month, 170 working hours at one working level. We say one working level mass. According to ICRP application 24 on radiation protection in uranium and other mines, in 1970s, ICRP established a task group to investigate radiation exposures in uranium mine and issued ICRP publication 24 in 1977. Although the focus was on uranium mining, it was noted that radium-226 is part of the uranium decay chain, which is found almost everywhere, and hence not limited to uranium mining. Note the rapid development of radon epidemiology and annual limit of the exposure to radon progeny of 12 working level mass was recommended. Okay? Subsequently, according to ICRP publication 65, named Protection Against Radon 222 at Home and at Work. In 1993, ICRP publication 65 established the use of action levels in terms of radon concentrations. For protection against radon in dwellings, selection of an action level in the range of 200 to 600 becquerel per cubic meter was recommended, corresponding to an annual effective dose of about 3 to 10 millisievert, assuming 7,000 hours per year spent at home. Protection in workplaces was considered separately from protection in dwellings, and protection against radon was considered separately from protection against other exposure to radiation. Action levels were recommended in the range of 500 to 1,500 becquerel per cubic meter, using the same annual effective dose basis of 3 to 10 millisievert as used for dwellings. Although the concentration is different. In the case of dwellings, 200 to 600 becquerel per cubic meter. At workplaces, 500 to 1,500 becquerel per cubic meter. But with a different conversion factor for workers and annual exposure time of 2,000 at work. This working hours. Furthermore, for occupational exposures, there was a reminder that a limit of effective dose also applied. 20 millisievert per year. These are general occupational exposure limits per year, averaged over 5 years, and 50 millisievert in any 1 year. This corresponded to 4 working level per year, averaged over years, and 10 working level in any 1 year. So how do we get these values? Based on minor studies, the nominal risk coefficient was estimated to be 8.0, 10 to the minus 5, minus fifth power. The unit is per millijoule hour and per cubic meter. So this is a time-integrated potential alpha energy concentration with SI unit based on the minor studies. Okay? We can rewrite in working level. This is 2.8 minus working level. can you convert?
From here to here.
2 days ago, we did this calculation. And here, we have to consider the determinant adjusted nominal risk coefficient in ICRP publication 60. The ICRP publication 60 tells the determinant adjusted nominal risk coefficient is 5.6, 10 gross second hour single. For workers, also for adult, second, for public, general public, 7.3. How do you get the dose conversion factor using these values? According to the ICRP publication 65, the dose conversion factor is called conversion convention. The unit is millisievert per working level mass. So you can calculate two conversion conventions at work and at home. Right?
So what is the difference between nominal risk coefficient and detriment?
This is a basic this is a basic radiation protection. You have to know. This is a basic knowledge on radiation protection. So you have to know.
So suppose that if the value is above 8.0 to 10 power minus 5, then we have excess amount of radon concentration in that particular area. Can we think in that way? Am I correct, sir? Am I correct? So for
Sorry,
example,
I don't understand.
sir, I mean, as per you were saying, it is nominal risk coefficient.
Yes.
Right?
This reflects cancer death.
Yes. So if the value, if I am observing a
Yeah.
particular area, radon concentration, if it goes beyond.
Wait a moment. If there is 1 million people here, 80 people will die with cancer. This is a risk coefficient. Okay? But you have to understand this. This is a basic knowledge of radiation protection. And here, So, in this case, this is minus cancer, lung cancer test. Here is every cancer, also any other radiation effects are included. Here, it could be different. Okay, so please calibrate. Let's start practice. Okay. At workplaces, how much received per watt level? At home, how much? The same received per watt level. Okay? Okay. Okay. So I'm talking about the history of radon dosimetry. This is a starting point. But several years ago, ICRP 115 was published. It says a different value, but the procedure is the same. Okay. This factor coming from uranium minus studies. Also, this is ICRP set this value, considering all the radiation effects, including cancer deaths and any other. So, look at the unit. And here, this is millisievert. Sorry, I made a mistake. This is 4.
I was looking at mine.
Yeah, sorry. This is 4.
That. Even
Minus 4 power.
There is no for
Yeah.
per, I think.
Yeah.
Huh?
Is it kind of 8.5 10 per minute per? Is it per?
Per W.
Yeah, sorry.
Yeah.
If somebody solve this calculation. Next. How much is it?
3.8.
So, but ICRP is a rounded one, so they use 4. Okay. Based on the epidemiological design. But actually, this risk factor based on minor studies is just for working workers. But they adopted for domestic exposures.
It's 5 millisieverts.
Yeah, 5 millisievert per working elements is at work. And at home, 4 millisievert per working elements. Okay.
Professor, one doubt, sir. Sir, one doubt. Last slide now.
Last slide. Yes.
That in home, the action levels are corresponding to 200 to 600 becquerel per meter cube. The corresponding annual effective dose is around 3 to 10 millisieverts.
How do you?
No, that is for public.
You don't understand.
No, that convention okay. But that's for public now.
Public, yes.
Public.
Yeah.
But in general, it is only 1 millisievert for public level.
Oh, this is another radiation protection system. It's a total limit. In the case of radon,
No, 1 millisievert is not from the natural sources.
2.4.
1 millisievert is for over and above natural.
Over and above natural.
Yes. And this 3 to 10 corresponds to a action level of 200 to 600.
But in that case, if you say 2.4 millibecquerel due to normal millisievert due to normal background, here this radon itself corresponds to 3 to 10 millisievert.
But 2.4 is a world average. It doesn't mean you cannot have 10 millisieverts of light.
In Kerala it will be more than that.
Then it is applicable to which region? The JRP says 3 to 10 is applicable to which region?
There are places where they have to assign some reference level, which are high, 600 becquerel per meter cube houses are there in some places. Now, they don't come under regulatory rule, it is natural. So then how do you set the level? So that is what ICRP guideline is.
And this, this
The
200,
lower limit is above world average.
200, 600, it varies again. It depends on the
I assume
country.
that 200 corresponds to 3 millisievert, and 600 corresponds to 10 millisievert, 3 times. You say the lower limit itself is above world average level. Well, lower limit 3 millisievert itself is above world
Yeah,
average
so,
level.
now,
How can you account for that?
Tanzania.
there are some percentage of places where you can have that. No? These are action levels, right?
Action level.
Action.
Action levels.
Action
See,
levels
some
are-
houses in Himalayan region can be well above that. Some houses in HBRA Kerala can have 40 millisievert, one or two houses.
Right.
So, but why do we need action levels? Why can't we have a recommended level?
No, we can't. It depends on country to country. Each country has its own.
Action levels, I assume that it is a dangerous level. Before
No,
that it
No,
is-
no, 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 no.
You are from DAE or you are from
Yes, yes.
You should know first.
No, no, no. It is not
See,
dangerous.
even the first statement you made, you should not have made. 1 millisievert per year is for facilities established by man-made sources. There is no limit for nature. There is no limit for nature. There is no proven evidence that natural radiation is harmful. So these are all precautionary guidelines. Not that there is a danger and there is a risk. But then yes, we have to take care in the interest of protection.
Finish? Okay. May I continue?
Sorry for disturbing.
It's okay. Use my time. This is a residence radon risk estimate from individual or pool analysis based on Anskia 2008. Probably Dr. Maya will give a talk on this.
Yeah.
Right? So, there are so many epidemiological studies, and at first, at the beginning, they carried out epi study individually, which resulted in large uncertainty. But after that, recently, they combined other studies. That means they got more numbers, good statistics here. Now, the data became more reliable than before. And this slide shows the relative risk of lung cancer versus long-term average radon concentration in the European pooling study. Here's a long-term average radon concentration in becquerel per cubic meter, and here is a relative risk of lung cancer. You can see there is a linear relationship between radon concentration and lung cancer risk. That's why WHO recommended the reduction of indoor radon. Even at the low level, we could see the positive result. Less than. So in ICRP 65, they recommend 200 to 600. But below, even below 200 becquerel per cubic meter, we could find the positive relationship. That's why WHO decided to issue the handbook. This data is based on the Darby paper.
Is it like this is a risk factor?
This one. This
So
one.
factor means, so if above this particular value, the risk is higher. Can I consider in that way?
So I think I will give us some rudimentary definitions and all of relative risk, what is, because these are all quantitative things, so maybe then you understand more. It's the ratio of risk. Right.
So after that, this is ICRP publication 115. So you understood ICRP publication 65. Yeah. 5 and 4, based on the uranium minor studies. But recently, in 2010, ICRP published another report on update estimate of risk, lung cancer risk associated with exposure to radon and exposure. This was based on epidemiological results from cohort of miners exposed to low levels of radon and for the first time from studies of lung cancer risk associated to indoor radon. This is the first time. So far, they didn't care about indoor radon. But after Darby's paper, North American paper, European paper, in this publication included the latest scientific papers on indoor radon lung cancer study. Also, they obtained more accurate results at low levels of radon. Okay? In the last publication 65, in this study, they don't care about, they couldn't take into account the low level of radon because there are large uncertainty. But this according to this ICRP publication 115, they consider at low level radon and also indoor level. This is a key point. The accumulative risk of lung cancer up to 75 years of age was estimated for lifelong non-smokers in a large European study as 0.4%, 0.5%, and 0.7% for radon concentration of 0, 100, and 400 becquerel per meter respectively. The risk to smokers was about 25 times higher. The same figures for lifelong smokers were 10%, 12%, and 60%. Please note that cigarette smoking is the most important cause of lung cancer. Radon is the second cause of lung cancer. An important conclusion of publication 115 was that determined nominal risk coefficient for lung cancer in a mixed adult population of non-smokers and smokers should be increased to 810 to minus 10 per becquerel hour per cubic meter. In other words, 1.4 cross 10 to minus 4th power per millijoule hour per cubic meter. Okay. This number close to twice as a figure recommended in ICRP publication 65. This is almost twice as publication 65. Taking into account these new findings, the upper value of radon reference levels was lower from 600 becquerel per meter to 300 becquerel cubic meter. Okay. The nominal risk coefficient of ICRP publication 115 is 1.4 cross 10 to the minus 4th power, and here this is all 1. The value is double. So please calculate, please convert to working level mass. I'm sure you can calculate. water.
Yes.
ಫ್ರಿಜ್ ಆನ್ ಉಂಟಾ ಫ್ರಿಜ್ ಆನ್ ಉಂಟಾ ಆನ್ ಉಂಟು ಆನ್ ಉಂಟು ಆನ್ ಉಂಟು ಆನ್ ನಾರ್ಮಲ್ ನಾರ್ಮಲ್ ಅಲ್ಲಿ 2-3 ಇಟ್ಟು ಅದ್ಭುತ ಬಾಟಲ್ ಉಂಟು ನಾರ್ಮಲ್ ಹಾಂ ದೀಪಕ್ಕೆ ನೀವು ಹೇಳಿದ್ರಿ ಅಲ್ಲಿ ಖಾಲಿ ಆದರೆ ಖಾಲಿ ಅಲ್ಲಿ ಖಾಲಿಗೆ ಹೇಳಿದ ಆಗಿದೆ
After you complete this calculation, it's 4. Almost 5. 4.96. Yes, okay, so almost 5. Lovely. Okay. So the answer is 5 plus minus
4.
Okay. But in publication 115, they adopted another determinant adjusted nominal risk coefficient based on ICRP publication 103. Cross minus second power perceived for workers for adults and 5.7 10 to the minus second power seatbelts for public. Okay? So ICRP publication 103 recommendation gives determinant adjusted nominal risk coefficient 4.2 cross 10 to minus second power per seatbelt for workers and 5.7 cross 10 to the minus second per seatbelt for public. Okay? So let's calculate again. At work, at home. Conversion convention. Unit millisievert per working level mass. So at work, at home. Okay. And 8.77. Rounded. Okay. let me summarize the conversion convention. In 1993, ICRP publication 65 gives us 5 unit is millisievert per working level mass, 5 millisievert per working level mass, and 4 millisievert per working level mass at home. In 2010, ICRP publication 105 gives another value, higher value than before, 12 millisievert per working level mass. At work, 9 millisievert per working level mass. At home, both are correct. The origin is different. Based on the epidemiological study, epidemiology is always developing. The last time, these are correct, but after several, almost 20 years, they got new findings. Then dose is higher. Okay.
Sir, can I ask a question? I
Yes.
didn't understand. So it is now 12 millisievert per WLM conversion.
Yeah.
And this change is coming because of
Yes, actually, we have new ICRP publication 137, 2018, 2 years ago or last year. They gives another value.
oh, I see.
At this moment, they supported this value. I will talk.
The basis.
Sir, I don't know, last time. There for concentration of 0, the risk is 0.4%. It means if radon is not there, then still 0.4% of risk of cancer is there. Does it mean like that?
This is zero becquerel per kilo.
Yes. I mean 0 becquerel is no radon there.
But naturally occurred.
Okay. Even if there is no radon, 0.4 is natural radon. Natural incidence of cancer. Natural incidence. Okay.
So after that, ICRP publication 1 to 6 was published on radiological protection against radon exposure. The most recent of fundamental recommendations of radiological protection were established in 2007 as ICRP publication 103. In 2014, ICRP publication 1 to 6 provided updated recommendations on protection against exposure using the 2007 principle and methodology and reflecting new scientific evaluation of radon risk from ICRP publication 115. So I just talking about this. This is almost 1 to 6. Sorry, I'm a little bit confused. This is 1 to 6. Before that, they adopted previous determinant adjusted risk factor. But anyway, 2004, 2014, this is a new value, this 12. That means, sorry, I misunderstood. So I have to be right. 1, this is 1 to 6. In 1 to 6, they adopted publication 103. But in 115, they still using what ICRP publication 60 value. Just 4 years, later, they immediately revised. So I'm misunderstood. Okay? Clear? ICRP publication 1 to 6. So I'm just talking about 1 to 6 from here. But previously, ICRP publication 65 is ICRP 115. In 115, they adopted, still adopted, well, publications, 60. But in 1 to 6, publication 1 to 6, they adopted new recommendation. New determinant adjusted nominal risk coefficient. Okay.
So that number 4 into 10 to the power minus 2 is very close to the atomic bomb survivor risk also. So this matched,
Yes,
radon
yes,
and this
yes.
were matched.
This bar is based on atomic survivors. Yes.
So that is
Okay.
After TDL.
間違えた。途中から大丈夫。
いや、
大丈夫じゃない。
あとです。
So, integrated approach for protection against radon exposure in all buildings is recommended. Whatever the purpose of the building, and regardless of whether the occupants are at work or not, the same reference level applies and protection should be optimized in all circumstances. The upper benchmark of around 10 millisievert per year from ICRP publication 65 continues to be recommended. Based on this, authorities should set a national reference level as low as reasonably achievable in the range of 100 to 300 becquerel per meter. Radon levels are compared to the reference level to help prioritize efforts to control levels in homes and most workplaces. me summarize this. The ICRP 65 is the action level. It's in the range of 200 to 600 becquerel per millimeter, corresponding to 3 millisievert to 10 millisievert per year. At work, considering occupancy time, working hours is 500 to 1,500 becquerel per year. 65 didn't differ to the difference level, the adapted action level. ICRP 1 to 6, they give the as a reference level is 100 to 300 becquerel.
So no reference, no action.
No action. Oh, no action level.
We call it reference.
Reference, you don't have obligatory
Right.
need to act.
Right.
But you should take note.
Right. They say as low as yes.
Yes.
So after that, ICRP publication 137 was published on occupational intakes of nucleus. Part 3 is really talking about radon. Although protection against radon is primarily based on measurement and controls of levels of exposure, those estimates are required in certain situations for workers. Those estimates are of value of protection purposes when workers are exposed to more than one source of radiation, as is the case for underground miners. In addition, those estimates are required for comparing sources of public exposure. Using the nominal risk coefficient from ICRP publication 115 and ICRP publication 103, those conversion convention value of 3.3 millisievert per millijoule hour per cubic meter for adults is obtained. This is fundamentally based on epidemiological evidence. On the other hand, using dosimetric models, the dose coefficient are 3.3 millisievert per millijoule hour per cubic meter for workers in mines and 4 millisievert per millijoule hour per cubic meter for sedentary office workers. Using the same methodology, the dose coefficient for exposure in homes is 3.7 millisievert per millijoule hour per cubic meter. For tourist camps and indoor workplaces where workers are assumed to spend 2/3 of time in exercise, the dose coefficients are 6.7 and 5.7 millisievert per millijoule hour per cubic meter, respectively. There is remarkable consistency between coefficients obtained by dosimetric calculations and conversion coefficient based on epidemiological comparisons. Taking account of both methods and their associated uncertainties, the following rounded dose coefficients presented in ICRP publication 137 are recommended. For buildings and underground mines, in most circumstances, the recommended dose coefficient is 3 millisievert per millijoule cubic meter. Hour is missing. Approximately 10 millisievert per watt meter. The corresponding dose coefficient expressed in terms of radon 222 gas exposure depends on the equilibrium factor between radon gas and its progeny. Using standard assumption of equilibrium factor of 0.4 for most indoor situations, this conversion coefficient corresponds to 6.7 plus 10 to minus 6 power millisievert per becquerel hour per cubic meter. While ICRP publication 137 does not specifically address public exposures, it is intended that this same dose coefficient applies to exposure in homes. Dose coefficient for radionuclide intakes by members of the public will be published in due course and will include radon. At this moment, they're just talking about occupational exposure with radon. But using the same methodology, we can obtain the dose conversion factor for homes. Using this dose coefficient, exposure to radon at upper value of the national reference level of 300 becquerel per cubic meter recommended in ICRP publication 126 corresponds to an effective dose of 4 millisievert at work and 14 millisievert at home. 300 becquerel per cubic meter correspond to 14 millisievert at home. For the specific situations of indoor work involving substantial physical activity and exposure in tourist camps, the recommended dose coefficient is 6 millisievert per millijoule hour per cubic meter, approximately 20 millisievert per working reference. In cases where aerosol characteristics are significantly different from typical conditions, where sufficient reliable aerosol data are available and estimated doses warrant more detailed consideration, it is possible to calculate site-specific dose coefficient using data provided in ICRP publication 137. How do we get 4 millisievert at work and 14 millisievert at home? To calculate effective dose, 6.7 plus 10 to minus 6 millisievert per becquerel hour meter 300 becquerel per cubic meter and close to 1000 hours. This is how much? How much?
4.02.
Okay. So the result here. 4 millisieverts. 4 millisieverts. And here this is the same calculation is 7,000 hours. Yeah.
Then the 300 becquerel per meter cube of radon or equilibrium equivalent.
This is radon concentration.
So there is no equilibrium factor in those.
This number
Oh, that is
includes
0.4.
yeah 0.4. Excuse me? What?
14.07.
14. Yes. Okay. So this slide shows the respiratory tract model, and this figure shows the regional deposition as a function of particle size calculated the human respiratory tract model for a standard worker. Okay. So respiratory tract are classified into 5 ET1, 1, ET2, capital BB, small BB, and AL. So just 1, 2, 3, 5 regions. Okay. You can find this figure in ICRP publication 66. So this is deposition, regional deposition positive. E1, ET, BB, capital BB and small BB.
This particular effective dose is for chromium. Annual effective dose.
And the effective dose,
This particular effective dose that we have calculated now.
this one. But this is the latest one. ICRP recommended. This 300 becquerel per cubic meter correspond to 4 millisievert at work.
I'll ask you.
So this slide shows the effective dose per working level months as a function of particle size calculated with the human respiratory tract model for standard worker the unit density and unit shape factor was assumed. Here the particle size and effective dose expressed in millisievert per working megahertz. If there are not so many smaller particles, those conversion factor are much higher. It depends on the area of deposition of particle aerosols. Aerosol particles. So this table shows the values of effective dose per unit exposure to radon 222 progeny calculated with the human respiratory tract model for different exposure scenarios. Adult at home without cigarette smoke, non-smoker's house, smoker's house, workplaces, indoor workplaces, with air conditioning on, with air cleaner on, and also mines. Here's a publication. Our papers are included here. This table was given in ICRU 88 report. So you see, we can see any small number like ICRP publication 65. But recently, we have large number now. Even the small quantity of radon give a higher radiation dose. So it's time to have a break.
Right.
Thank you very much. Yeah.
Good noon to all of you. So we continue with the topic, and a very important topic in radiation in general and radon in particular is the basis of risk. Because we are doing all studies, all measurements predominantly to be able to assess risks, which assumes there exists a risk. Not only that, it also assumes there exist quantitative numbers by which you can calculate the risks. So in the previous lecture, Professor Tokonami very authoritatively and very succinctly brought out the various complications that arise in actually converting a concentration of radon which you measure to risk that one observes. So you have different numbers. So how these different numbers come, if you see, it is because there are, first of all, it is a biological problem, it's a medical problem. Identification of the actually causes, cases. How many people have actually died. So it is disease, it is a disease-related problem. So first of all, then there is a measurement uncertainties that is coming because maybe the measured radon itself has variations. Then there is an uncertainty of its actual cause, the decay product, equilibrium factor. Then there are breathing uncertainties, the type of aerosol that is there. That is why the risk coefficient, the conversion dose coefficient varied by a huge factor, as you saw, of 140 to 20 at one level. So in no other subject you will have such a major variation for even assigning a dose per exposure as in radon. That's why radon is not equal or similar to gamma radiation problem. Just by having measured to convert to real dose is a major issue, lot of uncertainties. However, ICRP and UNSCARE have simplified them in order to make it applicable in a certain nominal or in a standardized manner, and that is why you have UNSCARE conversion coefficients which assume certain amount of proportions, typical aerosols and all. So what I do in this lecture is, we will not deal about the physical aspects of the uncertainties coming mainly from the aerosol problems. Maybe tomorrow I may give some idea of what is this aerosol radon progeny physics is about. Today I will dwell upon a very powerful method called epidemiological methods. All of you would have heard about it, but very unlikely anybody attended any epidemiology course, any class on epidemiology anywhere? Yeah, so this is a rare science generally taught in big cancer hospitals or in Tata Institute of Medical Sciences here, in Bombay, and some statistical institutes, which is central to radiation risk assessment. But radiation epidemiology is not statistics, it is not medical statistics, it's a very, very powerful, well-developed discipline in itself. It's a kind of low-profile work discipline, which is not as public as medicine is. So you don't hear about it, but every doctor respects epidemiology because actual data comes from there. So what is this epidemiology? For us who work in the context of radiation, it forms the basis of the system of those limitations that we talk about. That 1 millisievert per year for general public, when we say what does it mean and how that number has come, and 20 millisievert per year for occupational workers when we say what is the basis of this number. Those who are from nuclear industry would know, would have read it in some way, some place. Most of it actually codified in the ICRP series. ICRP 60, 1990 was a major revision on which most of these numbers are formed. I think more or less this number stays. And I would like to clarify here that there is a certain misunderstanding among general public, newspapers and press on this 1 millisievert per year. So 1 millisievert per year is not a limit for natural dose. It is only a regulatory limit for anthropogenic or industrial activity. Then you cannot expose the people at levels beyond 1 millisievert per year. But if somebody is already living in 100 millisievert or 10 millisievert per year, he is not subject to any constraint because he has been living. And there is no evidence.
Existing exposure scenario.
Yeah, existing exposure scenario cannot be subject to limitation. And secondly, this is not a limit for a patient. A patient, today X-ray CT scan is becoming one of the major alarming source of increase in the dose burden among world population. In America, it has gone 4 or 5 times higher than the normal background. It's very high because CT scan, since there is no limit for medical dose, some people, even for cosmetic persons, people like to get exposed to high doses. Still no limit it's being observed, but as far as I know, no limit has been set for any medical exposures because because radiation is not the main risk. Subject is being saved for some other bigger risk, so you cannot set limits. So these are the simple elementary things, but even these numbers are not random. They have come from epidemiological methods. So today I would like to not get into the derivation of these numbers, which is a separate topic, but what is this epidemiology? So I just want to give you a kind of flavor of the subject. So what is epidemiology? Fundamentally, it started sometime in 18th century as a discipline, and there is a joke which says that epidemiology was started by doctors who knew how to count, because most doctors didn't even know that maths. So some doctors knew some maths, so they started this job of counting the dead bodies. It's basically counting the dead bodies. So it is about studying the occurrence of diseases, their patterns and causes. Cause is a very, very interesting theory in epidemiology. It is not physics, where cause and effect are mathematically related. In disease theory, it is difficult to say what is the cause of a disease. Best example given is tuberculosis. Whether it is the bacillus which is the cause of tuberculosis or suppression of immunity in human beings is the cause of tuberculosis, you can always debate. The reason is 70% of human population carries the bacillus but does not get TB. You get TB only when there is a certain immunity suppression that takes place. So, right royally, one must say immunity suppression is the cause of the occurrence of disease. So, when somebody says radiation is the cause of disease, that cause has to be defined very, very properly. So WHO and UNSCARE comes to a decision to say that radon is today a cause of lung cancer. That cause has been debated via large statistical association, not a definite biological association, because there is still no biological mechanism which has been unequivocally proven. For infectious diseases, mechanisms are proven. For cancers, which are multifactorial diseases, which occur, multifactorial means many causes are responsible. So we have no way of finding out whether a particular disease has occurred because of radiation, and that is the problem. Just probably today people are able to say, doctors, that this particular lung cancer is because of smoking. I think that much has been achieved. But with respect to radiation, it has not been achieved, so one has to have statistical association. As a result of this, it is called an observational science. It is not an experimental science, because you are not allowed to do experiments. You can only observe populations. There is a habit, people do smoke, so you cannot stop them from smoking, but you cannot ask someone to start smoking. I want to study. So you observe people who are smoking versus non-smoking. It's a passive science, almost like these astrophysicists, they observe stars, astronomers. So it is like astronomers. You simply observe here what has happening in planets, but you cannot create them, right? So exactly. So it's a statistical, not a medical science. There is a misconception. Many people think it's a pure medical science, and some people think it's pure statistics. It's neither. It's a combination of both statistical methods and the knowledge of diseases. Often, but not necessarily, the epidemiology aims to establish cause-effect relationships via the statistical association with respect to specific agents. So before you start, you have to have a hypothesis, and the hypothesis is, okay, am I studying to find out whether smoking is causing lung cancer or not? So you have to make a hypothesis with respect to certain agent, and you have to specify one or couple of agents, but you have to pre-specify. These are my matrix of experiments. I am going to observe whether smoking and radon are going to synergistically affect each other or not affect each other. So you can have any level of hypothesis. Now air pollution is a major, for example, worldwide it is studied, and now for example the estimate is in India 1 million deaths are caused every year because of air pollution, which is 10% of the total deaths. It's one of the major causes. Compared to that, radon is still very much smaller level of risk is associated. So the epidemiology is fundamentally useful for generating a hypothesis which should be confirmed later through medical and biological research. So epidemiology is not again cause, you need not know. Famous example given is in Europe. All the 19th or late 18th century, just by observing that people were drinking water from that particular tap are all suffering cholera, malaria. I mean, these people breathing this, they are suffering malaria. Nobody had any idea of bacteria and viruses. Infectious diseases causes were not known. But by controlling via statistical analysis that predominantly these village fellows seem to be getting this disease more, infectious disease compared to that, because they are using that water, they started controlling and improving the health by knowing through epidemiological methods only. Not by knowing any injection, or it came much later. All antibiotics, everything development came later. So epidemiology had therefore a major role in public health through the 18th and 19th century in Europe. In fact, not many will know that in the 1980s, when the first AIDS cases occurred, nobody knew about HIV virus. Merely by association of certain habits of people, they isolated that people having these habits seem to get this disease. This kind of immunosuppression. It is a few years later that the HIV infection was discovered, but epidemiologists had a major role in identifying a group of diseases associated with certain lifestyles. So that is how epidemiology played that's why I call it as a low-key background science, but very useful in hypothesis. And for radiation, of course, it has remained the most powerful tool to establish, quantify risk. And one of the largest epidemiological study ever conducted on the world is that on the atomic bomb survivors. Largest cohort and entire knowledge of risk coefficients, including that of radon, is always strive to compare and see if it matches with that of the atomic bomb survivors. So that is what I will describe the science that goes into it. So for radon, ultimately it comes to how do you convert the absorbed dose to an effective dose, because as you may know, absorbed dose is a physical quantity. It comes from pure physics, energetics. But effective dose is not a physical quantity. Why? Why sievert is not physical but gray is physical?
Because it takes into account the radiation as well as the tissue weighting factors.
Correct. Principally because of the radiation weighting factor, which is half physical, it's slightly related to LET, but tissue weighting factor. So these factors are completely determined by ultimately a comparison of the absorbed dose to the observed risk. So it has to have an observation of a cancer, so biological disease effects. So that is why the effective dose is a radiobiological quantity, not a purely a radiation quantity or a biological quantity. It's a mix. So radiation weighting and tissue weighting factors. What are the issues? I am not going very systematically. I have a couple of slides, so I am going topic wise. So what are the issues when you do radiation epidemiology? One first problem is that cancer occurs in normal populations. We will see. In fact, there are so many problems with cancer is a major study, because why so much of first research is done on cancer? Because still we are not able to control it. I mean, it's a lot of improvement in medicine, but still not able to so-called cure it. Curing very, of course, there are quite a few cancers which are cured, but there are killer cancers which are not cured. However, it occurs, it has, most of it is connected with lifestyle, very little is connected with genetics, maybe 20%, 30% is genetic, but 70% is lifestyle factors, geographical variations, dependence on age. So there are so many issues to study, and a lot of so-called descriptive epidemiology deals with the study of cancer in populations. It's just the background. No, we don't make hypotheses. People ask questions like, if Italians in Europe have certain cancer rate, will the cancer rate be same for these Italians in America? Or will they reach American cancer rates after few generations? So this kind of research, so-called ecological studies, were conducted, and they have proved that eventually the normal population cancer rate approaches the background rate after one generation of migration change. Then finally the lifestyle is more important than genetic. I mean, that was the finding. So that is one problem, is that therefore it occurs everywhere, so to assign a cause is very difficult. Second is the so-called statistical fluctuation, which comes in small populations. After all, cancer is a rare disease. We don't have infinite resource also, you have limited funding. So you have to do research with a few numbers, some 10 cases, 100 cases, and then you have to have a very powerful statistics in order to be able to make definitive statements. I'll illustrate an example. So statistics play a major role, and what kind of statistics to use. So that traditionally cancer disease has been, in general the disease theorists, they use a Poisson probability, just as all of us doing radioactive counting also use Poisson statistics for counting. Same fundamental assumptions are made. So the fluctuation in cancer occurrences in any population is given by a Poisson rate. You can discuss that, what is the basis of it, but that's a very useful, at least, assumption to me. You have some guideline. Most significant significant issue is the so-called confounding. Confounding is, in fact, a major issue. All problems in many large epidemiological studies has been not accounting for confounding factors. So what is a confounding factor? Confounding factor is, if I am looking for the effect of radiation on cancer, but there are other diseases also, other factors also cause the same cancer, and if the population is exposed to that other factor, how do I separate the effect of only radiation? So here I think I am giving an example. Yes, here you can see what simple confounding, which is given there. Supposing I am starting with some 1,000 persons, in one group A, one study, whatever, it could be one region, say Bangalore region, and another one, let's say Bombay region, like that. In group B, 1,000 people and 1,000 people, you have started. And in 1,000 people, let's say I found 5 lung cancers in group A and 8 in 1,000 people in group B. Do I say that group B has higher risk? Because there are 8 in 1,000, there are 5 in 1,000. You find that radiation dose, supposing you measure, it is 80%, 80 millisievert here, and it is 150. Do I say that, okay, this is because there is more dose, so there is a radiation effect? Can we say, just by only relating to radiation, forgetting, assuming that other things are all equal, same people, same number of people, urban people, all city people, all males, all that you have done, you could still be misguided, because if you take the mean age of the population, it's so happy you didn't check that, but you found out later that that was only 45 years, and here the mean age was 55 years, and cancer is naturally is more among older people. In fact, it's very exponentially, it rises with age. People below the age of 35 almost minuscule, only pediatric cancers, leukemia, small children is there, but otherwise healthy group. It really rises after the age of 60 exponentially by a factor of 10 every 5 years. So you can have a large death of variations possible here. So, and further confounding could be also another factor which you might have to worry is there are 350 people in this are smokers and 500 here are smokers. Now that effect is another complication. So how do I make an assessment of effect of only radiation among this? So you have to create subgroups in this. Make list of smokers, make list of non-smokers, and with just 5 and 8 deaths, you might have to divide 1-0 numbers will come in each subgroup. So it becomes a very statistically complicated problem and may not get any result at all if you have only 1,000 subjects. So it may end up being very statistically insignificant, non-significant. Yeah, this is just give you a picture of how do we compare cancers in among different populations. So this is called age-adjusted incidence rate. You would see it in newspapers everywhere. Age-adjusted incidence rate is as high as 465. I suppose it is always for 100,000. So this is 465 per 100,000 per year. What it means is, if we choose a 100,000 people of a certain size distribution, not size, certain age distribution in a population, then 465 cancer cases would occur on an average in a year in an American San Francisco black population, for example, which is the highest. Whereas in a registry set up by Tata Institute of No. Not institute, Tata Hospital, Tata Memorial Hospital. So Tata Memorial Hospitals has set up lots of registries to examine whether rural India has lower cancers, for example, or comparable. So in a city, in a village called Barshi, it's slightly old data. Professor Badwe keeps talking about it many fora, so some are old. So you find the lowest. Now, you may say that, oh, maybe these are all very young people and these are all very old people, so I may be wrong. I could be wrong. But it is not like that. When you do age adjustment, it is done by projecting the age-specific cancer death rate to what is called a world standard population. They have created a standard which is called the healthy population, where the numbers have to have a profile, where the mean expectation of life is 80 years and large number of older people and a healthy population. So from every society's data has been transferred to a standard population and that number is given here. So this is not the crude observed number. You will not observe actually 465 in the San Francisco population. It is extrapolated and transferred to a world standard population, and that is called age adjustment, which is the first job that epidemiologist does. From the crude data, it transfers it into what is called as age-adjusted rate data. This is an illustration of how cancer varies with age. This is slightly old, constructed by us by combining Indian urban cancer data from various cities. So only for males right now, numbers are different for females, and you can see that the cancer rate, so there's a childhood cancer is an effect, slight effect, so it increases with age basically. One of them, this is world population, yes. The upper one is the world population from ICRP 60 numbers, and this is the Indian population. So it's cancer rates are less in India than the population. The fundamental reasons are not known, but generally a factor of 2 is the difference. Typically, today an American citizen or even the Japanese, I think the average occurrence of cancer is as high as, I think now it's more than 40% of the people die of cancer in advanced countries, I suppose. It used to be 25 to 30%, but 30%? 30% is the cancer. In India it is less than 10% still. Most people die of other diseases. The fundamental reason is that, you know what is the fundamental reason why there is less cancer? It is not because we are cancer resistant.
We are dying because of other diseases.
We are dying of other diseases. Other or infectious diseases are not ruled out. Number 1. Number 2, we don't live long enough to catch cancer. Cancer is an old age. Most people die. You know what is the expectation of life at birth in India? 60? 65. Somebody said 65. Yes. And for women? That is for women. For men it is 63. And in the world it is, I think, 80 for men and 85 for women. In Japan it's 80 or 85. So always as much as 5 years. So advanced countries, a signature of an advanced country is a woman must live at least 5 years longer than men. It's biological. So if there is a reverse, it means there is women are not taken care of well.
You're not happy at all.
Not a happy situation, yes. So these are the numbers. So our
diet, vegetarian and non-vegetarian. Do you think this affect?
For yes, of course. The Japanese population has much higher cancer, well known because of the meat eating. Deep fried meat was responsible. So that's one of the established cases of meat versus stomach cancer. So that's why people advertise vegetarian food now, saying that, well, it is less carcinogenic. I don't know the proof of that, but these are all heard. But this was one evidence that is there. Stomach
Generally,
cancer.
vegetarians are.
I won't. Maybe, but I don't know. I have no evidence at the moment. But
Sir,
yeah.
may ask this many a times in poor countries, this cancer-related death may go unregistered also.
Right.
Will that?
Yeah, I have lots of slides. Unfortunately, I couldn't recall them where they are.
Right.
It is the cancer registry is a major activity in the world. World cancer registries in advanced countries are very, very reliable. In India, since 1975, Bombay Cancer Registry tried to establish very reliable registry. One of the criteria of so-called reliable registry is to be able to detect the percentage of underreporting or misclassification. Diseases are not classified as a head, lung and all. They are classified as what in my time were called ICD codes. So now they have changed the number. I've forgotten. Modern doctors will know, slightly different. But basically ICD classification, 160 is lung. This much I remember. So ICD 160. So you have to, a doctor's job is to classify lung cancer in the ICD. But in India, almost now, they're insisting, but it is not done. In rural areas, in fact, relatives request doctors not to write cancer as the cause of death. So because of that, there is a huge misreporting which is there in many. So many registries are not reliable. But one of the best registries is the Bombay Cancer Registry. And the second, probably or equally best, is the Trivandrum Karanagapalli Cancer Registry, which came from the same TMH group of people, and last 30 years, Jayalakshmi, Nair and Gangadharan established one of the finest, most reliable registries with less than 20% underreporting of the cases. And test for this is the so-called ratio of death to the incidence rate ratio is an index to find out whether how much under-reporting is there.
Okay.
So there are many ways of finding out. So yes, that is one of the classifications. So age therefore is an important confounder. Any epidemiological study has to classify and first adjust for age, because age is a known cause of cancer. So you can call age as a cause of cancer, obviously, because as you age, you necessarily get higher probability of cancer. As you can see, for a Western population, when you go from 50 to 75 this age, your rate has increased exponentially from 100 to about 600-700 or something, into 100,000 per 100,000 per year. So that is the rate. So it's a large number. I just want to also give you the origin of how does one does statistics. This is not all, but this is just a hint. We know that when you count a radioactivity in a sample, we get a count. How do you do? How do you give standard deviation? But just by one count. There are many ways. One way to do standard deviation is you take large number of measurements, calculate the standard deviation. But hardly we do that in radiation. We make only one measurement. I got 100 counts. Then somebody asks, what is my uncertainty? What is the uncertainty if you have 100 counts? 10. Why? Why did you take square root? So it comes from the so-called Poisson fluctuations. Because Poisson fluctuation says that the standard deviation is square root of the mean. So you assume that whatever you have counted is the mean. So you assume then the standard deviation is square root of that and you get 10. So that is the basics. Same logic is applied for ATCs also. If in a certain population I have observed 100 deaths, I assume that intrinsically there is a death probability rate, which is the fundamental to a society. However, the observed death is a statistical expression of this death probability rate extrapolated to a group of individuals, and that extrapolation is identical to the radioactivity counting. That is, just as we assume in radioactivity that atom B does not depend on atom A. If atom A has decayed, it doesn't affect the atom B. Its probability of decay is still the same. Similarly, we say that if one person has died of cancer, it does not affect another person's probability of risk of cancer. Probability of risk of cancer, the a priori probabilities of risks are independent of each other. The moment you make the so-called statistical independence assumption, then Poisson statistics theory can be proved and you can estimate deaths. So as an example, I am telling you, I had the same group A, group B problem. Let us go back to that. I changed the number slightly. You had 1,000 people here, 1,000 people here. Here, let us say you observed 6 cases of lung cancer in A and you got 9 lung cancer cases in B. Can I say, and all other factors are now same radiation, there was a little, let's say, higher radiation. Can I say that this is because of radiation? Because other things now age. This also is 50 years, this also 50 years. Smokers, they are all equal probability. So for all what you know, they are identical population except differing for an age. Can I say that this 9 number, an extra 3 death I got is because of radiation? You cannot say. You cannot say not because of confounding, but because of because group B has a chance 3, of course you observe 3 cases, but the Poisson propagation of error tells you that error of a difference 6 minus 9, which is 3, equal to square root of the sum of the variances of individual occurrences. So it is the square root of 6 plus 9, because errors always add, they don't subtract. So you have, when you add, it's about root 50, which is about 4. So you have 3 plus or minus 4 actually, with 1 sigma. If you put 3 sigma, it is 3 plus or minus 8. So we do not, cannot assign a cause when statistics is against it. Does not give you a trend with the lower bound should be more than 0 at least. Here the lower bound is minus 1, which means that there is a possibility that radiation is beneficial to cancer. Maybe it is good for health. There is a negative risk. Less number of people are also allowed by statistics. So that is why you see many statements in radiation epidemiology being made to examine whether radiation is beneficial. It is called the negative cause of risk, negative risk, which is called the hormesis. Hormesis, radiation hormesis, whether it is allowed from the observation. So the question can be asked whether it supports observations support hormesis or not. So at 95% confidence limit or 99% confidence limit. So these statements are statistical, comes slightly advanced statistics, but basic idea is a Poisson error. Now, epidemiology, as I mentioned, is not just about occurrence of diseases or study of diseases. It is find out a cause. So how do you find a cause? How do you search for a pin in a haystack? As I mentioned, there is a lot of statistical fluctuation just because unexposed. Can I get some hot water? Just because unexposed people there are some deaths, and exposed people also there are some deaths. We cannot say that there are more deaths. You have to make a very careful analysis, and that is called a study design. I am only mentioning you two study designs. One is called a cohort study, and another is called a case control study. Cohort is a very classical study design, which is it's somewhat, I would say, it is also common knowledge. You would also do the same thing if you are asked. So if you are asked to find out, for example, whether smoking is cause of cancer, lung cancer, how will you start the study? Any ideas? You have to examine. So what you select a study population. Okay, let me tell you how one does it. So you select a study population, let's say region of Mangalore region. Then you categorize, you go to house survey, whether how many your husband smokes, because he will not tell, no, he smokes or not. So you'll ask why. There's a lot of tricks are involved. It's not an easy job to find out the truth. So, but then you do a survey, you find out how many people are smoking, how many people are not smoking, you categorize them. Then you follow through time. At 0 time, you have a certain population, you follow them. Every time a death occurs, you make a marking. But somebody may say that, man, tomorrow onwards I don't want to be part of your study group. So you have to account for these losses. But the fact that he was there for first 1 year of the study also is a data. Even though he didn't die, nothing happened to him. That is called a very interesting method of person year at risk. I will just give you an example of what it is. So you collect the risk base, then divide the observation. So go through time and record the incidence of diseases. Then establish what is called an incidence rate in the two populations after adjusting for confounding. Of course, you have to do all that complications. But let us say there is no confounding. Then you just find out how many cases of deaths occurred in one population, how many in the other population, what is the person year at risk in the first, person year at risk in the second. Then you calculate what is called an incidence rate and then take the ratio. That ratio is the risk factor. So I am telling you in words, but this is the way it is done. This is one method. It is very nice if a lot of money is there, like the atomic bomb survivor study is a cohort study, because the world community realized that until that time there was very little evidence for low dose effects, especially, or even radiation effects. Some radium dial-Painter's data existed, so they followed the population. Right in 1950, the LSS lifetime LSS group was formed, and large number of subjects, 80,000, a few lakhs of subjects were collected, and they were followed through. Every information on the society was obtained through available records, and even now the LSS study is going on. There are still, I think, 5% people are still alive, right? About that, I am forgetting the number, but certain percentage of Japanese population who are exposed are still alive, and the last part of the data is now coming. But by and large, that's one of the great large study that has given us our information. However, in many cases, you cannot do a cohort study. Because first of all, the disease, you may not have that resource, firstly, and already a statement has been made that so many people died because of a particular industry which is closed down today. But that has killed so many people. How do you make this ascertainment? You cannot now further study. You cannot select some people who are staying near the industry or staying far from the industry. But you have to still make a statement, an analytical study. That is a very beautiful, very powerful study design called case control study design, which goes back into the history, starting from an event or a collection of events that were taken place. So in the case control study, you collect all cases who suffered the disease in a study. First you go and find out how many people have died of, let us say, cancer, or maybe lung cancer, or leukemia. In fact, this case control study was used very powerfully to prove or disprove whether parents exposed to radiation workers, their children, whether they get leukemia or not, was a major issue in 1990. It is called paternal exposure versus childhood leukemia. Although originally they found by case control study that there is an effect by Gardner, later studies disproved it. So even though one study may succeed, second study may not, unless it is repeated by other studies, you don't call it a cause. So finally it was not considered a cause. But an example, that study is a classic example of a very well organized case control study, where the event had occurred but you have to find a cause. So you first find all the cases who have died of leukemia, then you look for controls. When you say controls, it is those similar type of, supposing it's leukemia, children below the age of 20, they call children, all cases of leukemia below 20, then you find out how many children of that age existed in that place. Then if the child who has died, let us say of the age 10, and it's a girl, you look for all children who are of age 10, who are girls, and who did not die of leukemia. So they are called controls. Those who have died of disease is called cases, those who did not suffer are called controls. So for each case you suffer a control. So you collect such controls, 3 controls per case. Then you examine then you go for who has been living near radiation institution and who has not been. You do it afterwards. Whereas in the cohort study, you first itself you divide who is the exposure person, who is not exposed. In case control, you do the exposure assessment afterwards by again investigations, and then determine what is called a relative risk after all the adjustments once again. So this is, for example, just to give an example, idea of how, it's a hypothetical, I just gave it for illustration for you, but almost studies will go like this. So we have, let us say we are looking at whether radiation is a cause of cancer. Let's say whether Indian atomic energy community is more at risk of radiation as compared to general population. It's a major question, and we did a lot of work on that, and newspapers keep writing that so many people are dying, no? Atomic energy, so many people are dying of cancer, their children are all mutated, you will get all kinds of rumors. So to actually prove it, you have to do a study. So how does it do? How do you do? You take an atomic energy employee, he's exposed, and take a control population from general Bombay city, all those people who are not in the atomic energy. So you call it as a general mixed category. Let us say you at 0 time, you take 10,000 persons, so 0 cancer deaths. Exposed to, that is atomic energy also, let us say you take equal number, but it is not necessary. You will not have 10,000 here, you may have 1,000 here, and you can take any number if possible. Later you will adjust, again 0 deaths. Then next year, you go back, how many people, 990 are alive, are present in the cohort. Now that 10 number less could be because couple of them died, couple of them have run away and we don't know where they have gone. But you need not call that as a total waste. 1 year average, their information is available, they are alive and not contracted because they are not among the 4 who are dead. So 4 cases have come out. So you collect the information of the existing database on that day as well as the number of deaths, again among the exposed in the same fashion. Quietly, I will keep following it up in a passive manner. Don't interfere, don't tell people, smoking chod do and all, nothing should be done. So at the end, let us say you collect what is called a person year. So this person year is a it's called the exposure. It's equivalent to exposure, but it is actually the data, total data. Why person into year is the risk? Some understanding is necessary. Why not person alone or year alone, and how it comes as a product? What it means, okay, I'll explain. It says that as far as the risk is concerned, 70,000 person year means either 70,000 people for 1 year has the same amount of risk as let's say 7,000 people observed for 10 years, it does not matter number of persons into product of time what matters, not individually. This comes from again the Poisson probability theory, that when the disease is small, the total delta y equal to, if you have a probability lambda, so if you have death probability lambda, so we know that delta n, the number of deaths that have occurred, is proportional to lambda into proportional to number of persons who are there at that instant of time into proportional to the observation time delta t, if lambda is constant, correct? So n into delta t is the product upon which depends number into time, and this is equivalent to person year in the entire epidemiology, and that is the basis of the concept of so-called person year at risk. It is called PYAR. So my mentor Professor Nambi, who passed away a few years ago, used to call it as we are doing cancer by PYAR method. So he used to PYAR, person years at risk. PYAR in India means love. So person year at risk is called the PYAR method of doing risk. So that is that's the basic risk factor. Now similarly you collect the person year at risk in the exposed population, you have observed 80 deaths. Then you calculate what is called as the incidence rate. Incidence rate is basically it's a mean incidence rate. It is the number of new cases that you have found among the existing population in that year. So incidence rate can here obtain your 70 deaths which have occurred in a person year cohort of 70,000, which means the risk is 0.001 per person per year. I understand the number incidence rate as per person per year. Or you can say what is the meaning of 0.001 per person per year, which means if I have 100,000 people, I have 100 cases of cancer deaths per year. So that is why normally it is given in 100,000 days, so that the numbers are integers. But theoretically, conceptually it is per year, per person per year. Similarly, you will find here it is 0.0012 per year. That will be 120 cases of deaths eventually from all this study per 100,000 people per year.
So when you say exposed, they are exposed to what level of?
Epidemiology, this is just I am giving you a crude method.
Okay.
Your exposure here could be, see, in epidemiology, exposure is an abstract quantity. Sometimes study can be done, argument's sake, whether Bombay people have more cancer as compared to Mangalore people.
Okay.
Here, the Mangalore you take as baseline.
Okay.
Then the exposure could be being in Bombay is the exposure.
Okay. It's a comparative.
There are many studies, for example, whether Parsi women have more breast cancer as compared to others. It's a classical study done by Mrs. Notani, for example. Their studies have shown. So there, being a woman is an exposure of some region. A Parsi community is an exposure. So exposure is called a categorical variable.
Right.
Now in the case of radiation dosimetry, I can further categorize exposure as belonging to dose of 1 millisievert per year and less, 1 to 2 millisievert per year, 2 to 10 millisievert per year. Each of them could be an exposure category. So this is done over scores of dose categories, and that is more sophisticated, but idea is call one as exposed compared to a background. So there are many studies. So now you can therefore, crudely you can say, you have a relative risk. Now it comes to the concept of RR, and relative risk is therefore, as previous speaker has very clearly been defining it via ICRT and unscared definitions. It is called RR. Relative risk is nothing but so-called, is actually should be done via the rate method, incidence rate in this case for cohort among exposed versus unexposed. Same thing for unexposed. So So it's a very, very important concept. And any RR minus 1, this is called excess relative risk. In epidemiology, excess relative risk is a very, very important concept because it subtracts its extra attributable deaths in the population because of the cause, whatever exposure is there. So for example, in this case, the RR is 1.2 and 0.2 can be called as ERR, extra. It has no dimension. Whereas incidence rate is dimension per year, and RR has no dimension. And ERR also has no dimension. Okay, so this is in a nutshell description of a cohort study. I have some examples of case control study. Just to give an example how that is done. I think you can tell me by how much time I have. So I
20 minutes you have.
I have another 20 minutes. So we will go through a series. So this is a case of a case control study. Pardon me, this is I took it from somewhere, one of the old teaching things, so may not be best in it. And it is nothing to do with radiation, it's a non-radiation group. I have presented this, so I just can show the basic idea is that you go back here. So you have a group of cancer patients called cases, and they are then compared with a group of those who have not got cancer, but otherwise you tend to match them. It is called a matched case control study. You tend to match as far as possible. Age, sex, area, many a time. It is if you are looking at a child, leukemia of a child, it is nice to seek a control from one of the family members of the child who have not suffered leukemia, of the same age and belonging to the same sex. It becomes much more well matched, better matched. Then you go back and look at the histories, and the most important history you look at are the exposure histories. How many among the cancer patients are exposed, and how many among the non-patients also could be exposed, should be exposed. In fact, otherwise it is a bad study. You must have exposure probabilities equally distributed, somewhat relatively distributed. More quantitatively, you create what is called a factor table. Here I am giving an example. A factor table is simple. This is just a one-dimensional table without bringing in any confounding. There are multi-dimensional factor tables when confounding is involved. One more axis of the confounder has to be put, but otherwise it's a very stratification it is called. You take an example of a total 1,100 population. Basically what I will tell you like a story. What happens is you find that there are 100 cases of, let's say, childhood leukemia in a district or a state. And you have to answer whether this is because of some radiation level, something. But you don't worry about the radiation level. First you take 100 cases. Then you find so-called controls. So, basically you have 1100, you have a total case, you have 300 cases have been collected. Then you, for each of the case, you find controls. Go to the house, select people, and generally you must have about 3 controls per case, but not necessarily. On an average, it should be something like 2 to 3, but every time you may not get. So every time you go and find what is the cousins of the child, same age, did she have cancer? No, then you take her. So like that you give that, let's say 800 controls you selected. So you now have a population of 1,100. Now you start looking for how many among 300 cases are exposed. Then you start investigating what is the radiation level they have been set up. The exposure could be above 5 millisieverts, something like that. How many are there if it is radiation? So you divide exposed and not exposed. As I mentioned previously, it can be a categorical variable, like belonging to a qualitative set or not, or it can be a mathematical numerical variable, like those above 5 millisievert per year and those below 5 millisievert per year could be non-exposed. So you divide and you find that 100 were, let's say, above 5 millisievert and 200 were below. It's possible. Then you take controls. Same thing you do, you find that 300 among the controls also were above 5 millisievert per year, but it did not suffer the disease. And 500 here could be among the controls are not exposed. So then of course this has to match. Then we estimate relative risk as a so-called odds ratio. Here the concept of odds ratio is coming. In fact, case control studies uses the word odds ratio as a measure of relative risk, and that is AD by BC. You multiply 100 with the 500, you get 50,000, and 300 into 200, I think it comes to 60,000. So odds ratio is less than 1. So relative risk is less than 1, which means that there is no attributable risk among the exposed people as opposed to unexposed. I just want to explain to you why odds ratio is relative risk. Here, there are two interpretations for this AD by BC quantity. So AD by BC can be written as so as I mentioned here, it's odds of being a case among exposed. If you look at exposed as a category, if there is a higher odd of being a case among the exposed as compared to being a case among the unexposed, that also implies agent as a cause of disease. So you can write AD by BC mathematically as one way is A by B. That is, what is A by B? How do you interpret A by B? A is case, exposed case, and B is exposed control. So it's odds of being a case as compared to a control. Odds of being a case among the exposed, as of odds is always the ratio of the two quantities, as compared to the odd of being a case among the unexposed. If odds of being a case means a cancer-ridden person, among the exposed, if it is higher, which means exposure is the cause of cancer. That is why that way of interpretation is also a risk measure. Another way of interpreting, so AD by B, can be written as A by B divided by C by D. Right? This is one way of writing it. Same thing mathematically can also be written as, another way is A by C divided by B by D. You can write the same thing. So, but the physical interpretation now is different. Here it is odds of being exposed among the cases, that is, odds of being exposed among cases is A by C. So if the odds are higher among the cases of being exposed as compared to the control, which means that exposure agent is causing disease. That is also a measure of risk. That is why the relative risk expression does not depend on how you interpret, but it just depends on the cross product of the two. So it's very easy to statistically analyze, and that is the method. So in this particular case, that odds ratio is less than 1, and one would say that you have to do a lot of statistics, of course, separately. That is a separate issue, but at least as far as the definition goes, this is less than 1. Now coming to radiation carcinogenesis, now that you have done a case control study or a cohort study, and you want to now make a statement whether radiation is causing the disease, and one of the fundamental definitions of causality is that if a particular agent is causing a cancer, then when you increase the agent, the effect also has to increase. So one of the causation theories is, when I increase the dose, then the risk should increase. If something is going wrong, then that definition or a risk should change. If not increase, there should be a change. It cannot be that when I increase the agent, there is no change in the risk, then there is something non-quantitative about it. And now when you say change, there are major issues, and this picture comes into picture. This is called the low dose extrapolation problem, but basically how do I fit? If I have an experimental data, I can fit either by a straight line, which is called a linear hypothesis. When I double the dose, my risk also increases double. So that is the linear model. Most used model, and all analysis, without the linear assumption, it is extremely difficult to run dosimetry protocols. So linearity assumption is conservative. However, data may allow what is called as a supralinearity, and also sublinearity, and also threshold. Threshold is a very, very important thing. Whether there is a threshold dose, and a lot of debate today is going on whether there is a threshold. Threshold means we know that for many chemical carcinogens there is a threshold, which is called TLV. threshold limit value. If you have sulfur dioxide concentration below some 20 or 10 microgram per meter cube, there is no effect at all, no harm. Whether radiation also is it similar? Below 1 millisievert per year, are we saying there is no risk? That is not true. Linear threshold hypothesis says that there is a linear no threshold hypothesis says that at any level there is some risk, but people are trying to see whether the Japanese bomb survivor data allows for a threshold. Below some dose, no extra has been observed. It's a matter of debate. So LNT hypothesis basically assumes a linearity, and the evidence like this, the reason comes because the experimental data are so scattered that you can actually fit many curves to it statistically, and very difficult to take a decision. So relative risk versus the increasing dose, one must then fit to some kind of a line. Very often linear model if you use, what it means is the excess relative risk as I defined here, relative risk minus 1 should be beta into dose, and beta is called the dose coefficient. And that is what we say when we say 5 into 10 to the power minus 4 excess deaths per WLM. When we say it is actually you are determining the so-called beta coefficient and in the case of atomic bomb survivors, where it first decided, it's given in terms of the excess relative risk per sievert. It is the excess relative risk per unit dose is the quantity beta. So now if you know beta, excess deaths, actual deaths can be computed as a difference between the total and the background, right? And that is by multiplying beta with the dose. And since relative risk means what? It is the risk of the study population with respect to a background population. So for the actual death you have to multiply by B naught and multiply by person years at risk. So here, baseline and TY, just was giving an example. So can you calculate in the previous example, we can do it here, this one, I got a background risk of 0.001 per person per year. I can, so this is my unexposed means control group. This is the background risk. I can use this and calculate expected deaths in the exposed group. Supposing the exposure did not have any effect, what is exposed deaths? 0.001 into 65,000. Just multiply, how many it will come to? This is 1 by 1000, so 65. You must have got 65 expected deaths. So you can calculate the expected deaths by multiplying the risk coefficient, the baseline risk, and from the population. So that is the example I was giving you. So then you can say excess death. So I expect 65 deaths. I can say the 15 deaths that I have seen are excess. I have to find a reason for it. Why they occur? Is it statistical fluctuation? Is it because of radiation? This is what epidemiology do. This way just discussed few things. Yeah, another important problem that comes in radiation epidemiology is a major difference between the low dose and high dose effect. This is an NCRP illustration taken with respect to animal studies, from an animal study. If you do a dose response of the induced incidence versus the absorbed dose, these are the data points you will see, and you find that there are good theory also which shows that actually it must have a linear quadratic kind of a behavior. At high doses the rates are different as compared to low doses. If you want to apply only linear theory, you don't want a non-linear curve like this, because how do you do dosimetry for a non-linear curve? How do you accumulate doses? How do you calculate? It's very difficult for operational health purposes. So you want straight lines. What do? If I use only the large data, I get a straight line which goes like this. But if I use the small dose data, somewhat coming from here, extrapolated curve, then I will get a straight line like this. So the Japanese A-bomb survivor problem was just this. We had very reliable data of people who are exposed to large doses, more than 1 sievert. most of the radiation workers to who or people living in the high background radiation areas, their exposure is less than half a sievert. How do I transfer the dose? I mean, how do I transfer the risk of large populations to small? So a lot of analysis is possible. One method is what is called dose and dose rate effectiveness. So a factor of 2, for example, is assigned by ICRP 60, which says that since the slopes are generally lower at low doses as compared to high doses, by decision, by a kind of collective mutual agreement between various experts, to decide on a number by 2. You reduce the risk factor by 2. The reason I am saying is that is why the observed risk coefficients in the Japanese population is twice higher than actually that is used in the ICRP, because all the risks have been divided by approximately a factor of 2 to account for the dose and dose rate reduction factor. This is of course general interesting knowledge. There has been a big debate on LNT proponents and LNT opponents. LNT opponents are of 2 types. There are 2 groups again. LNT proponent is normally the ICRP and the UNSCARE and almost regulatory bodies who decided that in the interest of risk conservatism, let us take straight line as the risk. Extrapolate the high bomb survivor, atomic bomb survivor data to low doses, and it's a nice precautionary principle, and it is supported by some other low dose studies. LSS at that time was supposed to be supporting it, and it is simple and easily explainable to public. So advantage is when the dose doubles, you simply multiply by 2. So you have to, dosimetry becomes very easy. Radiation measurement can be integrated. So you measure only the total millisievert. You don't have to follow through millisievert per year every time. Every day's dose you don't have to assign risk. You can integrate the whole thing because the product of the 2 dose rate into time only matters. So that's why LNT is used. But however, the opponents, they feel that because LNT is there, unnecessarily we are doing dosimetry. Actually radiation has a threshold, which means below some dose you don't have to monitor people. There is no chance of risk at all, unnecessary. We are not monitoring everybody for sulfur dioxide, so why monitor for radiation? So you are unnecessarily increasing the cost of nuclear power, so it's unnecessary. There is one group. There is other group which says that no, you are lowering the risk. Actually it is more than straight line. So you are putting everyone into harm, you are telling lies. So the so-called anti-nuclear lobby, they believe in supralinearity. So both the groups are in this. But these are more debates, and the convention today is to go by LNT, by and large. I mean, this just to keep you aware of the debates. So I probably maybe will continue later, but just to give you the sources we have are the 3, the famous Japanese risk study and radon among the U-. These are the 2 different studies. Let me tell you, the radon problem is actually different, very, very different from the atomic bomb survivor problem. There are 2 important things. When it comes to gamma radiation, most of the people were exposed to gamma radiation. Gamma radiation is a whole body exposure. Dose, and gamma is a low LET radiation. So almost 1, the radiation weighting factor is 1. Radon is a lung specific disease. Local exposures, although we call it as a low level radon problem, it is not a low dose exposure. Locally, because of the high LET, large energy is delivered. Lung exposes 1 by 0.12 times higher risk compared to the whole body. That is why the tissue weighting factor for lung is 0.12. So 10 times more. So as a result, radon studies have to be carefully done. When we say radon dose, as an epidemiologist, should not, it is only for regulatory purposes. We say 1 millisievert per year also for uranium mine as compared to, let's say, our reactor. It's only for regulatory, but actual epidemiology, you have to go for exposure, that is absorbed dose, and not for the effective dose. Lot of other factors, and that is why whereas Japanese bomb survivor study is considered the standard. This gives you some description. It's one of the largest study. Part of survivors of Hiroshima and Nagasaki. several, this I think, I'm sure there are many reports of 2004, 2010 reports also must have come out. Study population is 86,500. Major dosimetry revision occurred in 1986, quality is 86, and this has remained as a database, and I am aware of reviews I've been following up to the work of Preston et al. 2003. Study involves putting people in 36,000 cells. It is not a small. I mentioned about cells, age, sex, distance of exposure, confounding habits, various habits, community, ethnicity. You created so many groups, and there are supposed to be, you're doing analysis over 36,000 cells. That is the thing. And well, these are details. Let us skip this. So, for example, in an analysis by Pierce and Preston in 2000, major efforts were made to look at the low dose component of the atomic bomb survivors. High dose studies were already standardized, but now they were looking at low dose component. Those were exposed, peripheral exposures, to prove whether a threshold exists or not. Yeah. So this is the work by Shimizu or Pierce and Preston. Yeah. So 2003 also they did more analysis, but basically they said that virtually there is no evidence for a threshold. Even if it exists statistically significant, it is at a very low 0.06 millisievert or sievert, 60 millisievert and down, maybe there is an evidence, but that is one end of the exposure. It is not a median value, it is an extreme low probability line, and more or less LNT hypothesis is valid, especially by fitting at the low dose data less than 500 millisieverts. So this has been the study of Price and Preston, more or less. Yeah, 60 millisievert. Yeah, it has been any possible threshold will be less than 60 millisievert. This was their conclusion. There are many effects, radiation causes, different ways it propagates for solid tumors as compared to leukemia, all historical results. And here I want to bring it to your attention that although there are a total of 86,000 persons, amounting to about 10,000 deaths until the period 2003, where finally the database, effectively the entire dose limit is based on about 400 extra deaths which could be attributable to radiation, because the difference when you adjust and obtain, all the data is generated from these 400 deaths. So I would stop at this point, and maybe in a tutorial or something we can continue and connect to other things. So, yeah. Right, it's almost 1 o'clock.
Break for lunch. At the same time.
ಈ ಕಡೆ ಒಂದು ತೆಗ್ಬಿಡಿ ಸ್ವಲ್ಪ ಫುಲ್ ಬಿಲ್ಡಿಂಗ್ ಬರುವಾಗೆ.
The walking calibration chamber installed here is having a volume of 22.7 meter cube or 22,700 liters. So the detectors what we use for radon measurements are calibrated in a walking kind of calibration chamber in order to intercompare and derive a calibration factor to study its sensitivity factor response. So what we do here is we place the detectors inside, gas measuring detectors like pinhole dosimeters, radioic detectors, charcoal based canisters or vials, different kind of detectors. As you can see here, these detectors are placed in the chamber, right, at different positions. So we place it at different positions, even the monitors which needs to be calibrated. Then we give a particular condition of humidity and temperature as per the requirement for your detector. Like if you have a requirement for this humidity temperature condition, your detector needs to be calibrated, then that particular. Then we increase the concentration or give a concentration of radon in the chamber. We are using here soil gas as a source, and you can see in the monitors I have already injected radon inside. The concentration right now is 3600 becquerel per meter cube. Also here, these two monitors are the reference monitors what we are using. These are the secondary monitors. These are primarily calibrated alpha guard in BFS, which is a primary calibration facility. We get the primary calibrations of the monitor done there, or else from VARC, where you get a standard source and a standard atmosphere. We calibrate these detectors, and these will form the secondary units for us. Then other detectors which we try to calibrate in the chamber, we try to calibrate them with respect to these reference monitors. In case of passive detectors, we expose for different concentration durations. Then we derive a calibration factor. In case of active monitors, we give a percentage of deviations of these monitors with respect to the reference value. So this is how we do the gas measuring detector calibrations in the walking kind of calibration chamber. The main purpose of using a walking kind of calibration chamber is you can place large number of detectors and intercompare their performances.
But while doing for passive, we cannot do for active, because for active devices like radon or alpha guard or something, if we keep, we will do it for only for few minutes or like an hour, and we will take it out. But like for passive, we have to keep it for longer duration.
Yeah,
but
it depends on the specifications or the response time, all those details of your detector.
So while doing passive, we have to do only for passive.
Nothing like, you need a reference instruments will be there to have a monitor of the levels here. Apart from that, you can do it simultaneously, no issues.
No, but you cannot take the active
Immediately, like as I said, for passive there will be a certain duration of response time for which you need to expose it. After that only there might be a track formation or something. Your monitors, maybe if it is 10 hours, your monitors will give you a value before that only. In 10 hours it will give you a proper value. You can calibrate it or give a reference value. But in case of passive monitors, you have to consider its response time, build-up time, all those things, and then only you need to expose it for a particular duration.
So the question I think is, if it doesn't have a readout, if it has an automatic readout, it will store, right?
yes.
So you'll have 10 values.
But we need not to keep the active device for a longer duration.
If you can keep it, you can keep it. If no issues.
Not necessary.
Not necessary.
It's better to keep first calibrate the only passive devices separately and
As per the requirement, since it is a big instrument and lot of things needs to be taken care of, so we normally go for both the type of detectors together with the proper time interval which is set for taking care of the response time of the passive detectors as well as the monitors also.
You say something on the spatial homogeneity. That is very important.
We use this facility here. Before using these directly for the we cannot just simply deploy dosimeters at every point and inject and just calibrate. There might be difference in the concentration values at different points. So initially, there are characterization experiments associated with any instrument or so we do the characterization of these chambers, spatially how the radon concentration will be distributed when we inject and when the fan is on. Then is it proper? Is it okay to place detectors at each and wherever possible, whichever convenient place? Is it okay, or there will be a difference in the reading? So these are called initial characterization experiments. Spatial homogeneity we check by placing these detectors at different positions and seeing what value it gives from the reference value. So if it is not, then we either if with the fan off condition, if we get a homogeneity, then we go for that. Then if it is not there, then we try to have a homogeneity with the fan on condition for circulation. All those things.
Soil gas also.
We need to maintain it constant for calibration experiments. Actually, calibration experiments are in different kinds of modes, like something called as static mode or something called as dynamic mode or semi-dynamic. It means that the concentration level, how it varies in the chamber when you expose the detector. In a static mode, what you do is you just increase the concentration to one level, then you close all the inlets and outlets, possible path of inflow, and it will be like a decay. Radon will gradually decay, and in that duration, maybe if you increase the concentration to 10,000 becquerel per meter cube, until it comes to 5,000, it takes 3.8 days. Assuming those things, it is called decay mode. So you take an average value of those exposures and try to calibrate your detectors. Other than that, you have something called as dynamic mode, where you use a strong source and continuously pump in radon to maintain a level. It will be in, if it is 10,000, we try to maintain it in 10,000 becquerel per meter cube only and calibrate the instruments. Then apart from that, we have our own technique like semi-dynamic mode, where you just inject radon in an interval to maintain. You need not always, continuously inject radon for maintaining stability. You will get, by periodically injecting, you can maintain an average value, which is sufficient for calibrating your detectors, more than sufficient.
What about the decay progeny?
Progenies, since we are calibrating only gas measuring detectors here, we need to eliminate the progeny which is added by the soil gas. So we use different things, different adsorbers
Why?
like
Why?
so that the
Why you want to eliminate?
because these detectors will have sensitivities for.
They are closed detectors. They have a membrane, they have a filter. Only gas can enter. You need not worry about decay products. If you allowed decay products, normal decay products would have entered. So you are not allowing them. No, answer, I don't know, I may be wrong. So
There will be certain interference factors by the progeny.
Like what?
If it is adsorption kind of.
We are using silica gel. Most of the products in the
silica gel is for moisture. Excuse me, it may be a good practice, like a good hygiene practice, but there is no scientific reason why decay products should interfere with radon measurements. Because all the passive instruments, radon cup dosimeters, they are designed to remove decay products from outside. Either in the pinhole also there is a filter paper it removes, or in membrane it removes, so there no decay product can interfere. But maybe it's a good practice to control unnecessary unwanted decay products, so you can have them. But you don't worry, really you don't have to worry.
So what about the canisters or charcoal base where you just
But you are absorbing radon in that.
absorbing? But
You are
on the-
measuring radon. Right now we are sticking to radon, right? So even there also decay products. See, if you allow decay product, then normal decay products anyway are there. That also is uncertain. So you would have already caused enough harm in it. So since that you are tolerating, extra decay products, why are you worried? It need not be an issue. And by the way, from soil gas, decay products are unlikely to come. Why would they come? Right? Because their particles will be held back in the soil itself. So good practice.
Yeah.
But for gas, no. But decay product calibration, of course, that is a different story. That is somebody asked that question, how you calibrate, then it's a separate.
Sir, I understand the concept of calibration factors for active devices, but I don't understand it for passive devices, because we already have sensitivity factors, we have dose conversion.
What is sensitivity factor, by the way?
That is the sensitivity
Define.
of the film to radon or thoron.
You define. Don't tell me just sensitivity factor. We observe tracks. You want the concentration. So how do you get concentration from tracks?
Yes.
What you measure is tracks. You need concentration information. So you need a factor connecting concentration to tracks.
Tracks.
So that is called, normally if it is written as tracks equal to some constant into concentration, that constant is called the sensitivity factor. 1 by that constant, which is concentration equal to tracks divided by sensitivity factor. So 1 by sensitivity factor is called the calibration factor. So knowing sensitivity factor is the same as calibration. So it is just a reciprocal of each other. But you have to know it, otherwise how will you to a field survey. So through controlled conditions you measure, you estimate, assume that it will be valid in the field. That's it. But I wanted to ask, people can ask also, can you control humidity? And you must mention that. Humidity may have effect on calibration factor, especially if it is active instrument like RAD7, which will fail when there is a high
Humidity greater than
if the
20%.
silica gel is not saturated. Whereas the instruments like radon GEO will not fail even if you have high humidity. So to demonstrate that, you have to do varying humidity experiments. So maybe you can do like that.
These humidity is a very influential factor while you calibrate active molecules where humidity plays a role, such as RAD7. And in order to study the effect of these factors like humidity, even temperature, we need to control these conditions in the calibration chamber. So in this calibration chamber, we can control the humidity from 35%, 95%. And the temperature can be controlled from 10 degrees centigrade to 50 degrees centigrade.
Temperature also can be controlled. 10 degree. How do you do 10 degree?
Like compressor
Cooling.
cooling.
Temperature by compressor.
Temperature by the heater. Humidity by compressor.
Temperature by heater. And if we want to cool it, it cools out
It is
eventually.
actually a circuit, feedback circuit which is involved. Large circuits like compressor, heater, everything is there. You can see the temperature and humidity maintained in the chamber different display. So in order to maintain that, so many components work in the chamber. So that it's just that. But you need to maintain those things when you calibrate your instruments.
Ma'am, have you ever found a different calibration of sensitivity factor which other than the standard reported values we
No,
make?
those sensitivity factors, for example, for pinhole, those are like after the calibration experiment is being done. But maybe that time it was not a big chamber, walk-in kind. But
Concentration does not
those sensitivity factors are found. We also conduct experiments on those here, and the sensitivity
calibration is
factors
very
are the same.
So, for the entire Indian type of dwellings, the sensitivity factor
It is not for the dwellings, it is for the, one is detector type, other one is the condition, like humidity, temperature condition in the Indian environment. But when we finish our
नहीं अंदर तो
very nice for integrated
after that, I can show you these monitors and
because it integrates with 6 hours.
the experiments are going on. Because no, first there is a
अंदर
system
जितना
which
जा रहा है मुझे वहाँ पता चलेगा बाहर जो आ रहा है वो यहाँ
we need to on it. Then you can see by the concentration.
अंदर डाल रहे हैं उसका
What is the radon concentration?
और उसके कंपैरिजन में यहाँ
You ask, we show people how it varies, how much alpha gas shows, how much this shows.
So you can see the radon concentration right now present in the chamber. This is using RN2O, you can see here 4,300 plus or minus 2,855. And you can also see
How much is this?
4,850.
And that fellow is showing?
4,750.
Not bad.
And error there is 300.
Error, forget that. People write whatever. This is square root law they use and write. That I know how this is. We also write errors by a Poisson. But this is nice. So the agreement is good.
Yes.
This can do even for thoron.
It
If
can.
you have a mixed case. And that may not work. So what is the value?
48,000 you can see both out of 8.
underground,
4,000?
because it gives a lot of delay. All the thoron will decay.
4855.
Radon concentration.
If it's the concentration which is pumped into this particular chamber. And then that particular alpha got also reduced.
You can see the mode concentration, and this is in the diffusion mode. You can see
It is just in background.
it is not having a
20
pump
becquerel
there.
per meter.
It is just in the diffusion mode.
25, like
This
that.
is in the flow mode.
But usually if you measure at
So
the,
you keep your dosimeters like that.
near the soil test,
Oh, that is just.
we will get thoron concentration
So
of
how is-
50 kilobecquerel.
Here on the
So that is hanging. So this is the thoron mixed, all ends, right?
entry part.
Can you show me the other side of the dosimeter?
Yeah.
I want to see how porous and how open it goes. Because your controversy is raging. So we are more volatile.
Sir, redesign
I wanted to show you.
in the area 4855 and 47
You told something about
It absorbs humidity.
Soil gas.
Thoron is coming from that area. So that all the thorons are very yeah, decay out. So nothing is available in the chamber. It is what pure radon concentration. There are many conditions for different yeah, different concentration. For example, 10 kilobecquerel, 10 kilobecquerel. Depending on 60 kilobecquerel. According to that, weight carry out because we have two solutions.
Oh, that means we need both.
Here combined is this is one soil test. This is another soil test. What is connected together? So get very radon concentration.
There 4008.
Understood?
Standard deviation.
We are not going to measure in only two instruments. We have many instruments. We can keep all the instruments. Whatever results. We will show all the results.
You're not, no hands on?
We are seeing others. We will tell only after that.
Only this much or more is. So now the question for decay products, what will you? Supposing you want to calibrate for ERPS decay, tomorrow set up the chamber.
We have to have this aerosol project.
Must maintain an aerosol system.
They promised earlier, some trust, they will spare but spent my 4-5 weeks.
May not be ready, but maybe you can work on it.
Yeah.
You can standardize this nano aerosol generator, make it available, customize it, ask somebody to do it. A lot of work is
Right.
you might just, it should be possible.
So actually the count is actually 8,400 becquerel per meter cube.
Meter cube.
So can I can I suggest this particular as two working level gas radon gases?
Because you don't know the equilibrium. It is only gas concentration. 3,700 becquerel per meter cube of equilibrium equivalent radon, not radon alone. Including of the equilibrium factor of the progeny, which
Considering equilibrium factor of 0.4, 0.5.
since they have a very good fan, progeny concentration will be zero. That is why the dose coefficient varies. Even if you measure radon of 8,000, it may be far less hazardous than 1,000 becquerel per meter cube of radon with full equilibrium. If this is 10%, yeah, they vary. Radon alone is not anything. What is the equilibrium factor you are getting here? Have you measured ever? What equilibrium factor have you measured?
No, we try to do the project, but we don't get anything.
Because of the fan.
Because of everything is eaten by that.
Switch on the fan. So you run the fan until radon becomes uniform, close everything, then wait for an hour, 2 hours, then equilibrium factor will go up.
Sir, even low mode
You must use flow mode. Yeah, otherwise filters happen. That's only flow mode is good. Actually, I believe that it should work.
You can also introduce some aerosol agarbatti.
That later you can, but normal is enough. So much aerosol. Agarbatti and all complicated.
And she did a lot of this 3-count method, counting. She did enough.
With that, what the counts you are not see, you are not getting counts. They reduce 4 but I can say
Not zero. You have some count, but just like that.
but what is the flow rate? Let me ask some questions. Very nice. I have very good models to predict equilibrium factor if you know the suction rate of your. So you have
That flow rate is
how much is the flow rate?
360
RPM per
per minute.
No, mixing time.
Approximately same. So this
Meter cube
no
per
need
hour.
any kind of calculation. If instead of this it is like 3,100
Per hour. And what is the
plus
chamber
or minus
volume?
something like 100 becquerel per meter cube. Plus or minus 100 means either 2,900 or
2,700 meter cube
so this
per
much
hour.
of
So
difference,
per minute test I did.
like 1,000 to the difference.
Divided by 6,
They will be given
3,600
percentage. Maybe like this is the standard.
3,600.
4778 60 minus 61
So 60 minutes.
4778.
60 meter cube per
So 1 minute. So 1 minute.
This percentage
3,600 meter cube per hour is equal to 60 meter cube per minute. Do you agree? Its volume is only 22 meter cube, which is 1/3. So in 20 seconds, there is one air change. Every 20 seconds. Whereas 3 minutes is the half-life of
This
the
is one of the
fastest
types to find out the
radium. Even the radium will not be allowed in this area. So it's very high
ಈ
removal.
ಪೋರ್ಷನ್ ಏನ್ ಮಾಡ್ತಾರೆ
So you can model wise you can predict method factors. I have all the equations on I am typing it
actually
actually
15 minutes cycle.
because somebody sits with it and all the notes
It will up
and then we can have a small internal report and all because lab can keep it. Because all these things I have not written down and they are available in all schools here and there.
You should plan for
So if you
Yeah, I need
different type
someone
like
to write
50
down.
minutes cycle,
Yeah,
60
I
cycle.
will dictate.
After some time I am going to forget all these equations. Now still I remember all the equations.
Every 15 minutes you
Then
will
I
store
really look at
Store the data.
yes, Abu also does it now. Theoretically, not been taught. There was no time.
If we give a number of
My
recycle
time I learned.
also like
Liter various lectures.
so like 10
There is a connection of calculating
it will automatically goes for 20 it will stop.
compare with some theory.
That could be a publication.
At least knowledge application requires a little more sophisticated. I mean, everybody knows in the world. It is not that I am discovering it.
Just connect it by
Tokenomics group,
when you select this
Western world, any group has one person who will do all this.
procedure, then only it will start.
Our place we have, for example, 15 minutes.
This is the initial setup, 15 minutes cycle. Initial I will start. Okay, yeah, 15 minutes time.
only one time.
15 minutes, but again like an internal 0 to 15 minutes, and the 0 to 1 minute pump will be on.
And then stop.
It worked on the behavior of robotic product. Just in confined
Sample
environment.
input is collected.
Like posted off was 94 people, but it contains everything. Something, but it should be more detailed. He has not done calculations. You are living real chamber. In applications of the chamber can apply.
ಫಸ್ಟ್ ಎಕ್ಸಾಂಪಲ್ ಮುಂದೆ ಬಂದವರಿಗೆ ಒಂದು ನೋಡುವಾಗ ಗೊತ್ತಾಗುತ್ತೆ
Questions. Why 1000 becquerel per meter cube of radon can be more hazardous than 2000 becquerel?
Once again it will
I'm asking question.
Yes.
after 15 minutes, like
15
it is gradual,
But
but it will not show it as 16, 17, 18. Once again it will show it as 1.
2 to 8 to sensitivity range.
Yeah, 8 becquerel per meter cube to 50,000 kilo.
No samples, just connection. No, it will be actually.
Some more
I will tell you the
briefing you have to do.
situation.
Anybody have got any doubt?
You know the gap.
Some more doubt?
If you put the regulator, then it will be open.
No, you ask a
If
question.
you remove the regulator, it will be the same way.
We'll probe there.
If you
How many
connect
people will answer the question?
Yes, yes. Listen here.
I want you to calculate the working level for this. You have read the radon concentrations. What will be the working level? And if you want more data, you can ask any of us.
Yes,
If you can do without data, you will get a gold medal.
yes.
But if you want to do with data, that also is welcome.
Right,
And you have 10 minutes.
right. Do. So calculate the working level for this
From your-
existing concentration.
Your guesswork, whatever.
5,500 becquerel per meter cube.
Calculate working level, and you can ask the question is meaningless or we can't answer. Whatever answer is welcome, but we want to know your views. Please give your view on the working level.
5,500.
No hint, no more hint. Only JRFs are working level, SRFs don't work. Not working level. So a lot of jokes.
Working level is a standard. I mean, it is a standard.
No hint. You have to write, close it and show us. Don't probe ours. We will nod for every answer. I will agree with any answer, but only written is
Right.
ನಮ್ಮಲ್ಲಿ ಬಸವ ಹೌದಾ ಬಸವ ಅಲ್ಲ ಬಸವ ಅದು
ಹೌದು, ತಲೆಯಲ್ಲಿ ಇಡ್ತೀರಲ್ಲ. ಹಿಡಿದ್ರು.
ಅಲ್ಲ ಅಲ್ಲೆಂದಾಗ ಮಾಡೋದು ಯಾಕೆ
ಹೌದು.
ಅದು ಇವನು ತಲೆ ಮೇಲೆ ಅದಕ್ಕೆ ಹೀಗೆ
ಹೌದು, ಮಾಡ್ಲಿ.
Ten minutes, not much. 3:10 whatever.
Total potential short level
ये योगा वर्किंग लेवल का स्टैंडर्ड है.
Don't tell. I didn't ask you to convert. How many
The concentration is given to you.
Arey, meter is a standard, but your height is 1 meter. 1.5 meter. No? You can't say how many meters you are. You can't say it's a standard, sir. I understand.
No, see, you have the concentration value. Now you convert it to.
She says working level is a unit. How can you change? But she has, that's why I give the example of a meter. Now you should understand. So how many working levels are there? People like Krishnamani never understood working level. He always questioned why you need working level as if we discovered. Arrogance of that. Theoretical science can be combined with practical knowledge.
Problem they will understand faster.
Understood the problem.
This is 5500, no?
After 10 minutes, there is one more question. How much time they have? After what time you are doing? This session is a short time. 4 o'clock. So one more question you can ask. It is also nice. What do you think is easy?
It's correct. It's correct. One point 48. Yeah. Then he'll ask you another question. No, go, it's nice. Everybody is at same level, so go. 1.4. 55 divided by 37 is 9. divide by 37.
One working level equal to 3,700 becquerel per meter cube. And this much meter cube is the
So we can set only radon formation. We assumed you can several days.
we want only little field, but that way you can. One working level equal to this much concentration becquerel per meter cube. So we had told how much? 4,000, 5,500. How much? So cross multiply.
How much answer? That is closely
This is gas concentration. But we need progeny concentration. But here we don't have that.
This answer is based on assumption. And if we consider it exactly, you get it?
you should.
We don't have like it was
One from North India also done. You should represent the subject.
like it depends on our
Whatever is the answer, you can do.
evening we stay at the campus.
DRC source, known source of the Palau, purchased from Palau, Canada.
Stop. Okay, let me ask everyone. So what's your, you have only 2 seconds. What's your, you cannot get? You didn't get. Didn't get. Oh, good. So he wants some information. Better. That's correct. So okay, you got the answer. You should have asked, either you should have done a calculation saying that I am assuming complete equilibrium of daughter products, in which case the radon concentration is the same as the progeny concentration, equilibrium factor 1. So then I will have working level of 5,500 divided by 3,700, which is 1.5, something like 1.5. That is one correct, one possible answer. Another answer you can give is, sir, you are not given equilibrium factor, so I cannot calculate. So you could have said that, which is the same thing. Then I will say, okay, you assume equilibrium factor of 0.3 or 0.1, then you can read. So that is the idea. So correct answer is equilibrium factor should be given. But in the absence of such an information, you can make a judgment. You can ask, sir, is there a fan? Is there a suction? Then you will say yes. Oh, if there is suction, then I think equilibrium factor will be very less. So I will assume 0.1. Like that. It's a real world problem, I am telling you. So if there is no fan, room is closed, and is it very smoky? कोई खाना पकाता है क्या रूम में नहीं पकाता है कोई आ जाता ही नहीं, then the aerosol will be less, then the equilibrium factor will be high, around 0.8, 0.7. In the open atmosphere it is 0.8. So likewise you can make an assessment based on your knowledge of the subject physics. If you don't have data, you have to make a judgment. If you know nothing, then assume 0.4, because the whole world thinks it is 0.4, which is wrong, but that is what the assumption is.
0.4.
0.4.
That's the world average some
World
number.
average by answer.
Unscared. Very important. I want you to tell me the number of atoms of radon. Chamber volume is 22 meter cube. All that is given. Heard the question? All heard the question? You have to calculate the number of radon atoms in this chamber. Activity is 5,000 becquerel per meter cube. Let us see. You can also try. How will you calculate?